chapter is nitro compounds. Nitro group refers to NO2 group. The structure of nitro group is R N double bond O negative. Here nitrogen has positive charge because it is bonded with 3 electrons, but there are 4 bonds. But the capability of nitrogen is to have only 3 bonds. Now this negative charge, that is a lone pair on this oxygen, will shift its lone pair to this bond, and this bond will be shifted to this oxygen. So this oxygen will be negatively charged and this will become neutral. And this is the resonance hybrid, in which these two bonds are shown as partial bonds, that is dotted bonds. And separation of charges shown by delta negative here and delta positive here. Then we have nomenclature. The nomenclature of nitro compounds is done by writing nitro first and then the name of the parent compound. For example, CH3NO2. Here this is methyl group and this is nitro group. So the nomenclature will be nitromethane. Here nitro and then the name of the parent compound. Second example is CH3CH3. Here nitro group is attached to the second carbon. So we will write 2-nitropropane. This is the propane chain. And then the third example is nitrobenzene. Nitrobenzene. And then fourth example, this is 1, 2, 3. Now we will name the parent chain as nitrobenzene, but in the third position, or we can say in the meta position, we have an extra nitro group. So we will name this as meta dinitrobenzene, or we can say in IUPAC form 1,3-dinitrobenzene. Then the classification of nitro compounds. Firstly, RCH2NO2. When the nitro compound is attached to a carbon which is 1 degree, that is primary carbon, then the nitro compound is named as primary nitroalkane. When the carbon attached to the nitro group is secondary, that is 2 degree carbon, then it is called secondary nitroalkane. If the carbon is tertiary, to which the nitro group is attached, then it is called the tertiary nitroalkane. Preparation of nitroalkanes. Firstly, what are nitroalkanes? When a nitro group is attached to an alkane or a hydrocarbon by replacing one hydrogen, then it is called nitroalkane. The first preparation is vapor phase nitration of alkanes. That means alkanes are treated with nitric acid at 700 Kelvin to form nitroalkane plus water. This is called vapor phase nitration because it is done at a very high temperature, 700 Kelvin. This reaction has some limitations because let us take an example. Here propane, we added nitric acid at 673 Kelvin. Here a mixture of product is obtained. Here we got 1 nitropropane 25%, 2 nitropropane 40%, nitroethane 10%, nitromethane 25%. So we got a mixture. So this method is not used in laboratories, but this method is used for industrial preparation of nitroalkanes because we need industrial solvents only. The mixture of these all can be used as an industrial solvent. So this method can be used in industries. The second preparation method is action of silver nitride on alkyl halide. Here alkyl halide is treated with silver nitride. So we get nitroalkane and alkyl nitride plus silver halide. We get here alkyl nitride plus nitroalkane. That means this is because nitro group is an ambident nucleophile. So it attacks from both of its coordinating sites, that is either from nitrogen or from oxygen, to get two products. But nitroalkanes are the major products and alkyl nitride is the minor product. The mechanism of this reaction is, this is silver nitride. Here silver gives its electrons to oxygen to form NO2 negative, and from alkyl halide X negative is released, which combines with this Ag positive to form AgX, and this nitro group plus this alkyl group combine to form nitroalkane. The third reaction is oxidation of amines. This is a 3-degree amine and is treated with oxygen, that is an oxidizing agent, let's say KMNO4, to form 3-degree nitroalkane plus water. Then we have nitroarenes. Nitroarenes means when nitro group is directly attached to benzene ring. This is the phenyl group. When nitro group is directly attached to benzene ring, then nitroarenes are formed. Nitroarenes are prepared directly from nitration of arenes. That means if we nitrate arenes by using any nitrating mixture or something, then we will directly get nitroarenes. The nitrating agents directly used, which are generally used, are concentrated or fuming nitric acid. Secondly, the mixture of concentrated or fuming nitric acid and concentrated or fuming sulfuric acid. Third is the mixture of concentrated nitric acid and acetic anhydride, or we can use boron tetrafluoride instead of acetic anhydride. Boron tetrafluoride is BF3. Then we have acetyl nitrate, CH3COO, and the last, nitrogen peroxide in the presence of anhydrous aluminium chloride, AlCl3. Now, how do we choose the nitrating agent? That is the choice of nitrating agent. It depends upon the nature of compound to be nitrated. Either the compound is electron releasing or the compound is electron withdrawing compound. Or the second reason is number of nitro compounds to be introduced. For example, we want to prepare meta-dinitrobenzene or just nitrobenzene. Based on these two conditions, we choose the nitrating agent. The electron releasing groups are the activating groups. For example, NH2, OH, CH3. These reactions can be carried out at room temperature, and the nitrating mixture is used, the concentrated nitric acid is used. Or we can also perform some reactions in the presence of dilute nitric acid only. For example, phenol in the presence of dilute nitric acid can form ortho and para-nitrophenols. This is ortho-nitrophenol and this is para-nitrophenol plus water. Secondly, when electron withdrawing groups, that is deactivating groups such as COOH are present. COOH, or we don't have any group, for example, we take the example of benzene. To introduce more than one nitro group, or if we have electron withdrawing group, we are doing both of these cases together. Then these reactions are carried at a higher temperature, and the nitrating mixture used is concentrated nitric acid plus concentrated sulfuric acid. For example, when the reaction of benzene with concentrated nitric acid and sulfuric acid is carried at 373 Kelvin, this is 373 Kelvin, then we get meta-dinitrobenzene. But if the same reaction, that is benzene with the nitrating mixture, at 328 Kelvin is carried out, then we get nitrobenzene. So here we get different products at different temperatures. Now we look at the mechanism of nitration. The reaction is benzene in the presence of concentrated nitric acid and concentrated sulfuric acid gives nitrobenzene. The mechanism is, first step, generation of electrophile. This is nitric acid, this is sulfuric acid. When two H positive from sulfuric acid react with one OH negative, we get H3O positive. And from here NO2 positive is released, that is nitronium ion, and from here two molecules of HSO4 negative ions, that is two ions are produced. This is the generation of electrophile, and the electrophile is nitronium ion. In the second step, formation of carbocation ion takes place. That is, this nitronium ion attacks on the benzene ring, and it is a slow process in which we get these resonating structures and this resonance hybrid. Then proton transfer from carbocation to yield final product. From the carbocation, proton is transferred to HSO4 negative, and it is a fast reaction to get nitrobenzene and sulfuric acid. This is the final product. This is the product we need. Then we have the physical properties. Firstly, physical state. Nitroalkanes are colorless, oily liquids and have pleasant smell. They are sparingly soluble in water, but nitroarenes, they are yellow crystalline solids. Exception is nitrobenzene. This nitrobenzene is yellow oily liquid. Nitrobenzene has the odor of bitter almonds, and it is also known as oil of merbane. Then we have the solubility and density. All nitro compounds, whether nitroalkanes or nitroarenes, they are heavier than water. But nitroalkanes are sparingly soluble in water. That is, partially soluble in water. But nitroarenes are insoluble in water. They are readily soluble in organic solvents, because we know the principle like dissolves like, so they are readily soluble in organic solvents such as alcohol and ether. Then we have stability. When heated strongly, polynitro compounds decompose with explosive violence. Next is boiling points. Nitro group is highly polar, due to which they have strong dipole-dipole interaction. So they possess a high boiling point because it is difficult to break their bonds, so it is having a high boiling point than hydrocarbons of comparable molecular mass. And they are mostly volatile in steam. Then we have the chemical reactions. We know that nitro group is electron withdrawing group. For nitroalkanes, first reaction is acidic nature. When nitroalkane is treated with a base, say NaOH, it forms sodium salt of nitro compound. It is clear from this reaction that nitroalkane is acidic in nature, because when acid reacts with a base, it forms a salt. That means nitroalkanes are acidic in nature. Here, nitroalkane is having alpha hydrogens. That is, we can only use 1 degree and 2 degree nitroalkanes. This is because we will see this reaction and then we'll get to know why only 1 degree and 2 degree nitroalkanes can be used. Now, this sodium salt of nitro compound will undergo resonance. First, this negative will be transferred to this bond, and this double bond of nitro compound, nitro group, will be transferred to oxygen. So this oxygen will attain a negative charge, and when we do acidic hydrolysis of this in the presence of H+, that is the acidic hydrolysis, then we get Ac-nitro form. Ac-nitro form means on acidic hydrolysis the starting compound should form, but we have got Ac-nitro form of it. Ac-nitro form is more acidic than the nitro form. Ac-nitro form act both as an electrophile and a nucleophile. Then slowly it undergoes tautomerism to form a nitro form. This is the nitro form, and this is a slow process. Then from this we get the starting product, starting compound. The acidic hydrolysis of 1 degree nitroalkane releases carboxylic acid. When 2 degree is used, then ketones are formed. And when 3 degree is used, no reaction occurs. This is the reason why only 1 degree and 2 degree is used, because in 3 degree there is no alpha hydrogen, so the reaction is not carried out. Hence, this method can be used to differentiate between 1 degree, 2 degree and 3 degree nitro compounds. Also, we know that nitro group is electron withdrawing group, that is -I effect will take place. The next method to distinguish between 1 degree, 2 degree and 3 degree nitro compounds is the action with nitrous acid. When 1 degree compound is treated with nitrous acid, we get nitroalic acid, which dissolves in NaOH to give a red color due to formation of sodium salt. When 2 degree is treated with nitrous acid, then pseudo-nitrol is formed, which is blue in color and it is insoluble in NaOH. When 3 degree or aromatic compound is treated with HNO2 or nitrous acid, then no reaction takes place. That means this is because of the absence of alpha hydrogen in 3 degree and aromatic compounds. So we can distinguish between 1 degree, 2 degree and 3 degree on the basis of color. Here it is red, here it is blue, and here no reaction takes place. Then the third reaction is Mannich reaction. Here R2CHNO2, nitroalkane, is treated with HCH2, that is formaldehyde in the presence of ammonium chloride. And here we get nitroamine hydrochloride. This is nitroamine hydrochloride plus water. Then we have aldol condensation. When acetaldehyde is treated with nitroethane, we get 3-nitro 2-butanol. This is 1, 2, 3, 4, 3-nitro 2-butanol. The fifth reaction is reduction of nitro compounds. When nitro compound is reduced, it forms amines. When the reduction is carried out in the presence of hydrogen, iron and HCl, 1 degree amine is formed plus water. When the reaction is carried out in the presence of lithium aluminium hydride or hydrogen and platinum, then 1 degree amine is formed again plus water. But when the reaction is carried out in the presence of zinc and ammonium chloride, then alkyl hydroxylamine is formed plus water. Then we have chemical reactions of nitroarenes. This is a nitroarene. It forms different products when different catalysts are used. Firstly, we'll take the reaction in the presence of zinc, HCl, or we can use tin and HCl. Here, aniline is formed. Also, if electrolytic reduction is done in weakly acidic medium, then also aniline is formed. Now, if the reaction is carried out in the presence of zinc and ammonium chloride, aqueous ammonium chloride, then this is formed. This product is formed plus water. But when the reaction is carried out in the presence of zinc, NaOH, in the presence of CH3OH, then azobenzene is formed. Also, if we treat it with lithium aluminium hydride, then also azobenzene is formed. If we treat it with zinc in the presence of NaOH, then hydrazobenzene is formed. Then we have partial reduction of nitro compounds. This reaction is also known as Zenon reduction. Partial reduction means here, for example, meta-dinitrobenzene. We treated it with NH4SH, 3 molecules. It gives meta-nitroaniline. That is, only this nitro group is reduced to NH2 group, not this one. So this is partial reduction of nitro compounds. Also the byproducts are sulfur, water and ammonia. The electrophilic substitution of nitro compound, nitroarenes basically, is done using this method. Here we know that nitro group is electron withdrawing group, so it is a strongly deactivating group. It undergo electrophilic substitution reaction at meta position because it is a deactivating group under strong conditions. It only occurs at strong conditions. So let us take the examples. Nitrobenzene in the presence of chlorine and FeCl3. It gives metachloronitrobenzene. Metachloronitrobenzene. But if it is reacted with fuming H2SO4, we can see that all the reagents used, like chlorine in the presence of FeCl3, fuming H2SO4, fuming nitric acid, and concentrated sulfuric acid, these are all strong conditions. So its reactions are carried out in strong conditions only. Here, with fuming sulfuric acid, we get meta-nitrobenzene sulfonic acid, represented by this. Here, with fuming HNO3 plus concentrated sulfuric acid, we get meta-dinitrobenzene. Two nitro groups, so dinitrobenzene. Nucleophilic substitution. When nitrobenzene is treated with a nucleophile, in this case we have taken OH negative, it forms products at ortho and para position. So here we got ortho and para nitrophenols. This is ortho nitrophenol and this is para nitrophenol. Now the replacement of nitro group. This is a reaction. This is a polynitro compound. In case of polynitro compounds, that means in which more than one nitro group is present, one of the nitro group is replaced by the nucleophile. For example, when this polynitro compound is treated with ammonia, it forms para-nitroanirene. This nitro group is replaced by NH2 group. That is the nucleophile. If the reaction is carried in presence of KOH, then we got para-nitrophenol. That means this nitro group is replaced by OH group. Here, now if we take C2H5ONa, then this nitro group is replaced by OC2H5. So we got para-nitrophenol plus NaNO2 as a byproduct. Then we have mechanism of nucleophilic substitution reaction. Here we have nitrobenzene. When a nucleophile OH negative attacks on the ring, here it is attacking at the para position. This bond will shift here. From these resonating structures, we get nitrophenol. This nucleophile attacks at the para position and the hydride ion is removed. The last part of the chapter is picric acid. Picric acid is 2,4,6-trinitrophenol. That means 2,4,6,3 nitro groups. That means trinitro, and this is the phenol. So 2,4,6-trinitrophenol is called the picric acid. The preparation is done by firstly using phenol. Let's do its preparation from the first method using phenol. This is the phenol. When sulfuric acid is added to phenol, we know that SO3 group is attached. In this case, phenol 2,4-disulfonic acid is produced. That means the SO3 group is attached to 2 and 4 position. That means disulfonic acid is attached to this. Now when HNO3 nitric acid is attached, then we get the picric acid. In short, we have done the nitration using sulfuric acid and nitric acid to get picric acid. The second method of preparation of picric acid is from chlorobenzene. When we add nitric acid in chlorobenzene, two nitro groups are attached to chlorobenzene. That is 2,4-dinitrochlorobenzene is formed, and this compound is treated with aqueous sodium carbonate so that this chlorine can replace with OH. Again, this product we got in the previous reaction, and then the nitration of this product with the sulfuric acid and nitric acid gives us picric acid. This was 2,4-dinitrophenol. It is similar to the product we got in the previous reaction. Then we have physical properties. These are yellow crystalline solid. Picric acid is yellow crystalline solid. Its melting point is 395 Kelvin. Picric acid is sparingly soluble in water, partially soluble in water, and it is readily soluble in alcohol and ether because it is an organic compound, so like dissolve like. It has a very bitter taste. Now we know that its name is picric acid, but how this name came? Why do we named it as a picric acid? Because it has a very bitter taste, and bitter means picrose. So that's why we have named this as picric acid. Now the uses of picric acid. Picric acid is used as an antiseptic and it is also used as a dye for wool and silk. Used to dye wool and silk. It is used in manufacturing of explosives. We also use it to manufacture explosives. As a laboratory reagent, it is used for identification of polynuclear hydrocarbons, amines, alkaloids, etc. At the end, we have the chemical reactions of picric acid. Firstly, it is acidic in nature. This is because of 3 nitro groups. So, due to the presence of 3 nitro groups, it is very strongly acidic. Okay, firstly, we react picric acid with sodium bicarbonate. We get sodium picrate. This is a salt and this is a base. So, when base reacts with an acid, it gives us salt. From here, it is clear that picric acid is an acid. Also, it is clear from the name that it is an acid. Plus CO2 plus water. Then we have reaction with PCl5. When picric acid is reacted with PCl5, picryl chloride is formed. That means here in place of OH, we get chlorine. Picryl chloride regenerates picric acid on boiling with water. If we boil this picryl chloride with water, we again get picric acid. Reduction with Na2S. When we reduce picric acid with sodium sulfide, we get a reduced product. Its reduction occurs and we get picramic acid. What is picramic acid? Here, one nitro group is replaced by NH2 group. So it is a selective reduction. The last reaction is formation of picrites. This is picric acid. We've just drawn it in a different way. This is mesitylene. When these both react with each other, we get a charge transfer complex. So that was all about nitro compounds. Thank you.